Good morning, afternoon, evening, esteemed panelists. It's a privilege for me to have the chance to present my research paper. I'm James Samuel M. Alcaraz, and I'm eager to present my research to you today. I will now begin. The potential of cassava, Manihot esculenta, starch as an alternative biopolymer. Now, let's proceed to the chapter 1. With the adverse environmental impacts associated with conventional plastics, there has been a growing emphasis on seeking sustainable alternatives in recent years. Today, as environmental concerns escalate, there is a pressing need to explore renewable and alternative sources for plastics. Biopolymers emerge as a viable solution to tackle this global challenge, as they are derived from renewable resources. The utilization of traditional petroleum-based plastics poses significant environmental concerns, including pollution, depletion of fossil fuels reserves, and prolonged degradation periods. Conversely, biopolymers present numerous advantages such as cost-effectiveness, biodegradability, biocompatibility, and renewability. Statement of the problem. This study aims to produce bioplastic using cassava starch. Specifically, this study seeks to answer the following questions. Number 1. What is the level of biopolymer made out of cassava starch efficiency in terms of mechanical properties, water resistance, thermal properties, film formation and appearance, barrier properties, and biodegradability? Number 2. What properties does cassava starch have to produce bioplastics? Number 3. Is there any difference between traditional plastic and cassava starch plastic in terms of mechanical properties, water resistance, thermal properties, film formation and appearance, barrier properties, and biodegradability? Number 4. Based on the results and findings, what recommendation may be proposed? Objectives. Gen Generally, this study aims to produce bioplastic using cassava starch. Specifically, this study seeks to answer the level of biopolymer made out of cassava starch efficiency in terms of mechanical properties, water resistance, thermal properties, film formation and appearance, barrier properties, and biodegradability. Let's proceed to Chapter 2. Review of related literature and studies. Because petroleum-based plastic is not biodegradable, it poses a risk to the environment when used for food packing. Creating bioplastic from modified cassava starch will provide a workaround for that issue. Stated by Shamani et al. 2020. The creation of biodegradable polymers from renewable resources has advanced significantly in the recent few decades, particularly for those made from starch-based ingredients. From Surratt and Sangsit Hong research. Polymers derived from cassava starch offer a substitute that mitigates the utilization of non-biodegradable polymers derived from petroleum-based, has the potential to transform a sustainable cassava value chain. Light by Lilavin, Chakul, and Dioxan, 2023. It can be said that bioplastic made from cassava starch is more biodegradable than plastic made of polyethylene since it can break down into the soil in 45 days and won't cause pollution. Now, let's proceed to Chapter 3 with the flowchart of the methodology. Gathering of materials. The production of cassava starch as an alternative biopolymer will use 2 kg of cassava, water, a knife, a large container, a bowl, a blender, a sieve cloth, the starch extracted from the cassava, 1 liter vinegar, 100 milliliter of glycerin, water, a bowl, a heat source, measuring cup or kitchen scale, mold or tray, an oven mitt, pot, spatula, weights, water, heat source, commercial plastic, vape, flashlight, and soil. Procedure to extract the starch from cassava. First, we must wash the cassava to remove any dirt. Next, we must peel it with a knife and cut it into small pieces before transferring it into a large container. Finally, we must blend the cassava with water in a blender and transfer it into a bowl. Once all of the cassava has been blended, we can use a sieve cloth to extract the juice and collect it in an empty large container. After filling the container, leave it alone for a day. After a day, drain the water and use the sun to dry the starch that has accumulated at the bottom of the large container. Put it in the blender to pulverize the starch after it has dried. Procedure to produce biopolymer. Using the measuring cup, we must first measure 1,200 ml of water, 300 ml of cassava starch, 100 ml of vinegar, 100 ml of glycerin in a large bowl. Then bring some water to boil in the pot. Once the water is boiling, place the large bowl over the pot and use the spatula to constantly stir the mixture. The liquid will become more viscous after a few minutes of stirring, indicating that it is suitable for molding. Pour the mixture into the molder or tray and let it sit for over a week for it to be ready to be used. Procedure to test the mechanical properties. We need weights to test the film's tensile strength to see how resistant it is to stretching and breaking. Put the weights above the biopolymer and observe how much weight it can hold. Compare it with commercial plastic. Procedure to test the water resistance. To examine the film's ability to withstand water and absorb moisture, we need water. Observe if the water passes through the biopolymer. Procedure to test the thermal properties. To ascertain the melting behavior and the thermal stability of the film, we need to observe how much it withstands high temperatures. Preparation procedure to test the film formation and appearance. To assess the film appearance in terms of color, transparency, and uniformity, which can be visually inspected, we need to compare it with commercial plastics. Procedure to test the barrier properties. To evaluate the film's barrier properties against gases and light, we need smoke from a legalized vape user and a flashlight. Procedure to test the biodegradability. To conduct biodegradation tests to assess the film's ability to degrade under controlled conditions, mimicking composting or soil environments, we need to put some portion of the biopolymer under the soil, under the water, and inside the shelf and check the state of the biopolymer from day 3, day 5, day 10, day 15, day 20, day 25, and day 30. Gathering of data, statistical treatment, analysis, interpretation of data, and summarization. Now let's proceed to chapter 4. These are the results of the test. The mechanical property test. The table above shows the limit of the biopolymer made from cassava starch. The biopolymer can take up to 9.50 kg, while the commercial plastic can only take 8.25 kg. The biopolymer shows that it is more durable and flexible than commercial plastics. Water-resistant tents. Table 2 shows that the biopolymer made out of cassava starch can withstand water, warm, cold, or moist, cannot penetrate or pass through the biopolymer. Thermal property test. Look at the table above. Even with the product conduct on fire, freezer, in boiling water, cold water, and sunlight, there is still room for development if you want to use it for many years. This product continues to be a useful replacement for plastic that contain a lot of chemicals. Film formation and appearance comparison. In terms of film formation and appearance, biopolymers based on starch, such as cassava starch, frequently produce films with variable transparency and subtle surface irregularities. Commercial plastics, on the other hand, usually result in smooth surface, homogeneous, transparent, or translucent sheets. Commercial plastics come in preset colors. Starch-based polymers allow color customization through the use of natural additives. These distinctions between starch-based polymers and traditional plastics emphasize their unique qualities and possible uses. Barrier Property Test. The test provides simple and accessible methods to assess the barrier properties of bioplastics made from cassava starch by evaluating its ability to resist the permeation of smoke and light. Smoke test. Gases-like smoke cannot penetrate or pass through the biopolymer. And in the light test, due to its thickness and translucency, the bioplastic lets in very little light. Lastly, biodegradability test. This table provides the percentage of biodegradation observed from bioplastic from starch over various durations in both soil and water environments, offering insights into its degradation behavior under different conditions. Overall, the combination of higher microbial activity, nutrient availability, oxygen levels, and favorable physical conditions in soil environments promotes faster biodegradation of starch-based bioplastics compared to water environments, while in its shelf life, the biopolymer only shrinks. Discussions. Cassava starch is a popular raw material for the manufacturing of bioplastics because of its abundance, biodegradability, adaptability, compatibility, film forming ability, and potential for renewable energy. This makes it a sustainable substitute for traditional petroleum-based plastics. Bioplastic derived from cassava starch surpasses commercial plastic in durability and flexibility. It forms a robust barrier against water, regardless of temperature. However, it exhibits drawbacks in thermal properties and film formation and appearance compared to traditional plastics. Despite being thicker, its barrier properties closely resemble those of commercial plastic. Regarding biodegradation, further enhancements are necessary for it to withstand diverse environmental conditions. Now, let's proceed to Chapter 5. Summary, Conclusions, and Recommendations. Summary. Bioplastics derived from cassava starch is a sustainable alternative to traditional plastics due to its renewable source, biodegradability, and low ecological impact. However, further research is needed to improve its scalability, cost-effectiveness, and mechanical properties. It is recommended that businesses adopt a cassava starch-based bioplastics due to their environmental benefits and potential to reduce plastic pollution. Infrastructure investments, consumer awareness, campaigns, regulatory frameworks, and innovation are also crucial for widespread adoption. Conclusions. Bioplastic derived from cassava starch is a promising alternative to traditional plastics due to its renewable source, biodegradability, and low ecological impact. Further research is needed to enhance its scalability, cost-effectiveness, and mechanical properties. This could significantly reduce our reliance on conventional plastics and contribute to a sustainable future. Recommendations. Bioplastics made from cassava starch are recommended for businesses due to their environmental benefits and potential to reduce plastic pollution. Prioritizing research and development initiatives to improve mechanical strength, flexibility, and shelf life is crucial. Infrastructure investments for large-scale production and recycling facilities are also necessary. Governments, businesses, and academic institutions must collaborate to support consumer awareness campaigns, regulatory frameworks, and innovation. This will help reduce dependence on fossil fuel-based plastics and promote a sustainable future. That's all. Thank you.